Hi, everyone. Welcome to another supplemental, this one for lecture 6 on some new simple systems. There are some calculations that I wanted to do, but that didn't fit neatly in the main narrative of the videos, and so I've put them here into this supplemental video. The two examples that I want to work on are one involving the diatomic ideal gas, and then one involving the Einstein solid. Okay, so with that roadmap out of the way, let's get into something that I said in the video, which is that it's harder to raise the diatomic ideal gas's temperature than it is to raise the monatomic ideal gas's temperature. So let's try and figure out what we mean by that. Suppose that we have two boxes, and this one has a diatomic ideal gas in it. And this one has a monatomic ideal gas in it. Otherwise, let's suppose that these have the same characteristics. So they are both in the same state, UVN, or I should say the same thermodynamic state, same state in their respective phase spaces. Okay, and we want to know if we do an adiabatic work operation, on each system with the same quantity of work. Maybe I should say, if we do the same amount of adiabatic work on each system, which will have a greater change in temperature. Okay, so how do we answer this question? Well, we need to look at what the internal energy and entropies are of each of these. And when I say the internal energy, it would make sense to look at it in terms of the temperature. Okay, so let's do that. Recall that S is equal in either case to NKB times the log of sigma times V over N times U over N. And then I'm going to say to some constant little a. Okay, and then plus, now we're going to add some constant here, and this constant in either case turns out to be a plus 1 times NKB. Now, just to remind you, for the diatomic ideal gas, A was 5 halves, so that A plus 1 was 7 halves. Whereas for the monatomic ideal gas, A was 3 halves. Wonderful. Okay, and we know how to use this to find the temperature. We'll just use the fact that 1 over T is equal to the partial of S with respect to U while fixing N and V. Maybe I'll say V and N just to keep the order the same as we've been using. And we've done this calculation a bunch of times now, so it should be relatively familiar. But just to reiterate, NKB, this factor here, is multiplying everything, so it just gets pulled down. Then this log of a product can be re-expressed as a sum of logs. One of those logs is log of u to the a. Log of u to the a is equal to a times the log of u. And so in the end, we get times a times 1 over u, since 1 over u is the derivative of the log of u. Great. What all this implies is that u is equal to nkb times a times t. Okay, good. So this is one of the equations that we're going to need to answer this question. The other one is actually just the entropy. And let me explain what I mean. When we do adiabatic work, we know that we will do some amount of work and that will change the energy and the volume, but leave S fixed. Now, in this case, we'll be sort of directly acting on the volume by maybe compressing or expanding the box, but the result will be a change in the internal energy. So we don't really need this equation except to say that whatever work we do goes directly into a change in the energy in this case. Now, when we do adiabatic work in this way, we're changing the volume while leaving the number fixed. So W will also equal delta NKBAT, which will in turn equal NKBA delta T, since the only thing that's changing in that equation is T. And so there we basically have it. If we do a fixed amount of work, then we get a change in delta T that depends inversely on A. Maybe that becomes clearer if I move it to the other side. So let me finally do that. So we see that delta T is equal to W over NKB times A. So because A is in the denominator here, this implies that the diatomic ideal gas is quote unquote harder to heat up. That's just a little example that I gave in the video, but wanted to draw out a little bit more clearly. Okay, the second system I'd like to take a look at is the Einstein solid that we looked at in the last video. And I'd like to treat it a little bit more carefully than we looked at it there. Okay, so let's begin with the equation of state. And our main goal in this section is going to be to find the energy to temperature relationship and maybe take a look at it more closely. So the equation of state, I'll remind you, is going to be that S is equal to U over little u naught plus 3n times the log of U over u naught plus 3n minus U over u naught log of U over u naught minus 3n times the log of 3n. And once again, u naught, that is to say little u naught, is just some intensive constant that depends on the material, it turns out. Notice also that we have one internal energy coordinate u and one work coordinate n. So this is, in some sense, a simpler system than the ones that we've looked at so far. Okay, now the way that we'll treat this is just like we've done in the past, although 1 second, I've gotten ahead of myself. This really should be S over KB. I put the factor of KB on the left-hand side just to clean things up a little bit. The reason that matters is because now when we take the derivative of the right-hand side, it won't be equal to 1 over t, but rather 1 over kBt. So we have that 1 over kBt is equal to the partial derivative of S with respect to u while fixing n. And this we can treat with a couple of applications of the product rule and the chain rule. So let's do this first term first. All right. We'll treat the first factor of that term first. Just taking its derivative, we get just 1 over little u naught. And then we just copy down our log term once again. For the second term of the first term, in other words, when we treat the second factor in the product rule, well, we'll just copy down our u over u naught plus 3n, and then take the derivative of the log. Now, if we were to just take derivative of log, we get 1 over the argument, so that's 1 over u naught plus 3n, but then we need to use the chain rule. So inside of the log, u is multiplied by a factor 1 over u naught. So we need to multiply this by that factor in the numerator. The second term, which I'll mark here in red, is going to be very similar. And I'll just make sure to make those associations obvious. So for the first term, we'll get 1 over u naught log u over u naught. And for the second term, oh, and I forgot my minus sign. For the second term, we'll get u over u naught times 1 over little u naught over u naught by the exact same argument as before. Now we see that a couple of things cancel. In particular, this u over u naught plus 3n cancels with this u over u naught plus 3n, and this u over u naught cancels with this u over u naught. Now we have a 1 over u naught attached to a plus sign in this term, and a 1 over u naught attached to a minus sign in this term. And so those two terms totally cancel. In the end, we just get that this is equal to 1 over u naught times the log of u over u naught plus 3n minus the log of u over u naught. And maybe now you're starting to see the solution mechanism we're going to use. We need to move this little u naught over to the other side. Then we can combine these two logarithms and then exponentiate both sides. Let's combine the logs in this term, or in this line, sorry. We'll get 1 over u naught times the log. Now, because this is a log of a difference, a difference of logs, it becomes a log of a quotient. So we'll get u over u naught plus 3n over u naught. But notice that we could be writing this thing as 1 plus 3n over u naught. Wonderful. Okay, let's go a couple of steps forward. So we'll get u naught over kbt. In fact, let me skip that step entirely. We're just going to multiply this 1 over u naught. I should say we're going to multiply both sides by u naught. Then we'll exponentiate both sides. So we'll skip right to e to the u naught over kbt is equal to just the argument of the log. So 1 plus 3n over u naught. And now we're basically home free. We need to move this 1 to the other side and then cross multiply. And we finally get u is equal to u naught times 3n over e to the u naught over kbt minus 1. Good. Now, this is a pretty strange type of function, maybe one that you haven't encountered before. And so it pays to sort of try and take a look at it. First of all, we see that it has type energy as it must, because 3n has no type. Nothing in the denominator has type, and u naught has type energy. So we're good there. Furthermore, it's extensive because 3n is extensive and everything else is intensive. So u has all of the properties that it should have, which gives us some confidence that this makes sense. Okay, now that we have some sense of the type and extensivity of u, let's focus on taking the limits. So we want to look at both the high temperature case and the low temperature case. It turns out that the high temperature case is a little easier in the sense that there's not very much we can do to it. So, the low temperature case is not very difficult in that there's not very much we can do. Okay, so in the low temperature case, we merely get that u naught is much greater than kbt. And that means that e to the u naught over kbt is much bigger than 1. So all we can do is ignore the factor of minus 1 here in the expression for u, since the other term will dominate. It will be much bigger. So we'll get that u is equal to 3n u naught times e to the minus u naught over kbt. And I should say it's approximately equal to. Sorry. And this is about all we can do. This limit turns out to be much simpler than the high temperature limit. That said, by studying the high temperature limit, we can actually get a lot of interesting insight. So this is going to be the case when U naught is much less than kBT. And at first glance, one thing that you might think is that you can now simply Taylor expand this, but since it's in the denominator, things become a little hairier. Okay, what we're going to want to do is look at this function, u of x. And that's actually, I'm going to say curly u of x, which by definition is going to be equal to 3n u naught times 1 over e to the x minus 1, and where x is by definition equal to u naught over kBt. So x is much less than 1 in our case. And that means we're going to want to Taylor expand around x. The problem, as you can see, is that e to the x minus 1 as x goes to 0 is equal to, it goes to 1 over 0. So the limit is simply not well defined here. So the only thing that we can really do about this is try to multiply x by a polynomial and then Taylor expand that object. So we're going to try to Taylor expand x times u of x. Good. You know, actually, let me, just to clarify everything, let me get rid of that prefactor. So we'll have to remember to bring it back in later on. But we really just want to look at this thing now. Okay. So this thing is equal to x over e to the x minus 1. Because as the limit as x goes to 0, this is of the form 0 over 0, we have a hope that we might be able to solve this by L'Hopital's rule in terms of the limits. So let's first look at the limit as x goes to 0 of x u of x. Okay, so we'll need to take the derivative of the numerator and find that that's 1, and the derivative of the denominator. And without too much effort, we see that that's just e to the x, since the minus 1 doesn't contribute anything. So that's the limit as x goes to 0 of e to the minus x. But this is well defined. This function is defined at x equals 0, and it's just 1. All right, great. So we have the first term that we wanted. Next, if we want to Taylor expand, we want to look at the first derivative of this object. So now we want to look at the limit as x goes to 0 of d dx of x u to the x. Sorry, u of x. Okay, so this is going to be the limit as x goes to 0 of, and now we'll need to use the quotient rule. Okay, so just to remind you, the quotient rule, the derivative of f over g is equal to f prime times g minus f g prime over g squared. All right, let's get started. So in the numerator, we'll start with f prime g, which is just e to the x minus 1. Then we'll get f times g prime, so minus x, which is f, times g prime, which is e to the x. Now, all of that is over e to the x minus 1 quantity squared. All right, let's simplify this. So we're going to get 1 minus x e to the x minus 1 over e to the x minus 1 quantity squared. Good. Now let's see what happens if we set x equal to 0. In the numerator, we get this becomes 1, so it just becomes e to the x minus 1. But e to the x minus 1 is e to the 0 minus 1, so we get 0. In the denominator, we clearly get 0 squared, which is 0. So again, we have something of the form 0 over 0. And we're going to need to contend with that and see what we can get. Okay, so let's use L'Hopital's rule again. Now, the derivative of the numerator is going to require the product rule. So we get minus e to the x for our first term. And then 1 minus x, and then the derivative of e to the x, which is just e to the x. So 1 minus x, e to the x. Then next we would get the derivative of minus 1, but that's just 0. Then that's divided by 2 e to the x minus 1, but then times e to the x. And we see that we get a cancellation. Every term here depends on e to the x. So this is now just equal to 1 minus x. And I'm missing something. So it should have been minus 1 plus 1 minus x, so just minus x over 2 e to the x minus 1. Great. Okay, so the next order of business is to do this again, since we still have something of the form 0 over 0. Let's add our limit back in. Okay, so now in the numerator we get minus 1 when we take the derivative, and in the denominator we get 2 e to the x. But now we're in business because this has a well-defined form. This is just equal to minus 1/2. Okay, and just like that, we've done enough to now write down what the Taylor series is. So this implies that x u of x is approximately equal to, well, the 0th order term, which was 1, and then minus the first order term times x, so 1/2 times x. Now what I could do is bring this x from the left-hand side over and get a series expansion that way. So this would imply that u of x is approximately equal to 1 over x minus 1/2. Now let's rewrite u using this. So u is therefore approximately equal to, well, we'll need to multiply by 3n u naught. And then let's restore x is u naught over kbt. So this gives us kbt over u naught minus 1/2. Or in other words, 3n kbt minus 3 halves n u naught. Awesome. Okay, so now we can comment a little bit about this. Notice that this is linear, just like the ideal gas. But the coefficient of t here, rather than being 3 halves nkbt, is 3 nkbt. I should say either 3 halves nkbt or 5 halves nkbt. This is a totally new coefficient. We'll see how those are derived later on. We also see that this depends on this 0 point energy, minus 3 halves n u naught. And, that won't have a lot of physical effects, but it is interesting nonetheless. So down here, I've included a plot, and I'm realizing now that I missed a u naught here, of approximately what's going on. So this blue curve is the full curve that we would see over all temperature ranges. And the green curve is the high temperature approximation that we just derived, which looks linear. And the orange is the low temperature approximation, which diverges quite quickly as the temperature grows. We also see that the crossover point is right here, where kBT is equal to U naught. That means that U naught has some sort of special status within the theory. And it's interesting to think about what it could mean that there is this special, seemingly important constant that comes from the material. Now, the reason to go over the Einstein solid in so much detail is just that it's our first example where we don't have a simple relationship between U and T. This is one of the ideal gas properties that's very sort of cooked up, that we arranged the entropy of the ideal gas such that it depended on the log of U, so that there was this nice proportionality between U and T. But in general, we won't get that, and we'll have to take things like limits in order to analyze these cases more easily. But we will often see linear behavior of U as a function of T at higher temperatures, and when we get to StatMech, we'll see why that is. That's all I had for this video. Thank you so much for watching, and I'll see you in the next one.